All right, so with the Heisenberg uncertainty principle, you may be familiar with this term, but what it's essentially telling us is we can't precisely know the location and the speed of an electron. And one way you can kind of think about this is if you think about a wave. So if we were trying to figure out like the speed um, of a ripple in the water in like a lake or something, excuse me. Um, what we could do is measure how long it takes that wave to get from one point to another, and then just measure the distance, get the speed that way. Um, but if we only take a small distance, we're not going to have a very accurate measurement there. And it's kind of the same idea with the electron. If we're trying to get a really good um, idea on the speed of the electron, we're going to have to kind of observe it over a relatively large space. So we're not going to have a firm grasp on the actual location of it. So we can't know both of these things precisely at once. And then with the location of it, we're going to see there's going to be a couple of equations that are going to go kind of higher level than what we're really going to look at, but they're going to lead us into what we're actually going to focus on in the rest of this chapter. But if we think back to the previous one, we said electrons could behave as waves and particles. There's going to be quantum mechanics is going to be what can actually kind of describe that. So you may have also be familiar with Schrodinger or Schrodinger's cat. But with these quantum mechanics, if we look, way too far. There we go. With this Schrodinger's equation, it looks like some of this stuff just didn't get formatted properly for whatever reason. But this equation, we're not going to do anything with it in this class. If we wind up taking physical chemistry in like a junior level chemistry course or something like that, you may go into what this actually is. But essentially, what this is going to help us sort of describe is the location of an electron over time. And what we're going to see is when we take that equation, we're going to have it's known as a probability density map, which is essentially just going to give us the likelihood of where that electron is going to be located. And then with these maps, we're going to see that they're ultimately going to be giving us what we're going to refer to as orbitals. And these are essentially just going to be where the electrons are actually going to be located. And then with the quantum numbers here, we're going to see there's going to be different terms that we can actually use to describe the different orbitals where these electrons are going to be located. Because as we get to larger and larger atoms, so as we go from hydrogen to helium, helium to lithium, beryllium, boron, carbon, and so on, with each of those elements, as we increase the atomic number, we're getting an additional proton. We're going to have an additional electron along with that. So we're going to see that the electrons are going to continuously get higher and higher in energy. And we're going to see that they're going to be in different orbitals. And the quantum numbers here are going to be one way we can kind of describe those electrons. And with the quantum numbers, we've already kind of talked about the principal quantum number n, essentially sort of the energy level. So if you think about a general diagram of an atom, typically we've got the nucleus and in the middle with the protons and the neutrons, and then it kind of has the rings around that nucleus, sort of like the planets around the sun. Each of those rings we can think of as an electron shell, which is just going to be one of these principal quantum numbers. So that first ring would just be the first electron shell. Second ring is the second one, and so on. So we're going to see the principal quantum number is just going to be some whole number, starting with 1, and just as we move further and further from the nucleus, we'll just have that quantum number increase. And then the second one, the angular momentum quantum number, L, this is going to describe the shape of the orbital. So we're going to see different orbitals are actually going to have different shapes, and it's going to be based on this quantum number. And you can see them down here. So a quantum number, or an angular momentum quantum number of 0 is going to refer to an s orbital, 1 for p, 2 for d, 3 for f, 4 for g, and we'll see the difference between the first 4 of those. But with the quantum number here, this can be equal to n minus 1, or 0 to n minus 1. So if we think about a principal quantum number of 1, 0 to n minus 1 would be 0 to 0. So on that first energy level, we're going to see that we're only going to have an s orbital. If the principal quantum number is 2 now, 0 to 2 minus 1 is really 0 to 1. So we'll see on the second energy level, we'll have s and p orbitals. And as we continue, principal quantum number of 3 means that this can go up to 2. So the third energy level will also have the d orbitals involved. And then with the principal quantum number of 4, now we can start to get the f orbitals involved as well. And that's going to be as high as we go. But with this, it's 0 to n minus 1. So for the third principal quantum number, for instance, that's going to be 0 to 2. So we'll have all 3 of these first ones. So we'll have S, P, and D there, not just D. We'll have all 3 of those. And then the last two quantum numbers, magnetic quantum number. So this is going to be m sub L. And with this, again, this is going to be an integer. This can go from negative L to positive L. So if we go back here for a second, depending on, and I should mention, this is going to describe the orientation of the orbital. So we're going to see with like PD orbitals, they're going to be a certain shape, and then the magnetic quantum number here. This is going to tell us exactly how that's sort of oriented in space. So sort of what direction is it's pointed almost. But with it, these are going to be from negative L to positive L. So if we go back, that means for an s orbital, negative L to positive L would just be negative 0 to positive 0. So with the s orbital, we're going to see that there's only going to be one s orbital, just because we're going to ultimately see it's going to be a sphere, so we can really only have a sphere pointed in one direction. And then with a angular momentum quantum number of 1, that means the magnetic quantum number can be negative 1, positive 1, so negative 1, 0, or 1. So we're going to see with p orbitals, there's actually going to be 3 of them. With the d orbitals, negative 2 to positive 2, now we've got 5, because again, we're also counting 0 in there. So negative 2, negative 1, 0, positive 1, and positive 2. And then the final piece here, the spin quantum number, so m sub s. This is either going to be positive 1/2 or negative 1/2. Those are going to be the only 2 values we assign to this. And essentially, this is going to tell us the direction of the spin of the electron. And as we start to go through this, we'll see a little bit better how all of these are going to be connected. But like I just mentioned with the s orbitals, these are going to be spherical. So that's why when we go from 1s to 2s to 3s, we're only going to have a single orbital in each of those. Just because if we think about the magnetic quantum number, how are we going to orient this? You can think about this ball here. You can think of it like a ball, rather. And we can kind of turn that however we want. But since it's going to be a sphere, it's going to be uniform, so we can't really have it pointed in any specific direction, if you want to think about it sort of like that. And then with these, you can see as we go to higher energy levels, and again, that just means the electron is going to be further from the nucleus. That's why we're seeing the size of this orbital expand. And then with the equations, again, we're not really going to dive into those at all. But again, these orbitals are just showing a probability density, so the likelihood of where that electron is going to be located. And what we're going to see is as we move to those higher energy s orbitals, there's going to be what's known as nodes. And these are just going to be locations where the electron just can't possibly be located. So with the first one, we don't have a node, so there's no spot where it can't possibly be located. But then when we get to the 2s orbital, we've got a single node there. With the 3s, now we've got 2 nodes. And we're going to see that the number of nodes for the s orbital is just going to be equal to n minus 1. So if we had the 4s, we'd see a third node, 5th s, a 4th node, and so on from there. Okay, and then the p orbitals kind of look like two balloons just tied end to end. And this is actually showing the probability density there. So you can see we actually have a node in between those two. So we can see the likelihood, the region where that electron's likely to be located. And then there's a space in between them where there's just no possibility for it. So we've got a node there. And with these p orbitals, so we're going to have a angular momentum quantum number L of 1 here. So that means the magnetic quantum number can be -1, 0, or +1. And that's why we've got 3 different orientations here. So that's why with the p orbitals, we're going to have 3 of them. And if you look at the picture here, P usually goes px, py, pz. So this is just arranged a little bit differently, but it doesn't actually matter because we're going to see all of these are going to be equal energy in terms of these 3 p orbitals. But to distinguish the 3 of them, we've just essentially call them px, py, and pz because we've got each of these orbitals now just on one of those axes. So if we think about a graph, typically it's got x and y, but now the z axis would just kind of be, if we're thinking about x and y being on like the plane of the whiteboard or something, the x-axis would just be coming out of the border going into the board itself. But again, we just got the 3 orbitals because L can be 1, so that the magnetic quantum number then could be -1, 0, or +1. And then with the d orbitals, we're going to see something similar. It's kind of just like 2 p orbitals combined. So now we've got 4 of those lobes together. And with these, this means the magnetic quantum number, or the angular momentum quantum number L is going to be 2. So when we think about the magnetic quantum number, then it could be -2, -1, 0, +1, and +2. So we could have 5 orientations here. And then you'll notice 4 of them are just going to be those 4 lobes together. And with them, you can see these 3. So YZ, XZ, XY. This is just going to be in the plane of those axes then. So YZ is in the plane of Y and Z. XZ is in the plane of X and Z. X and Y, same thing. And then x squared minus y squared. Now we've actually just got those on those 2 axes. And then the 5th one's a little weird. It's just going to be 2 lobes on the z-axis. And then we're just going to kind of have a donut circling around the middle there. And then with these orbitals, if we were looking at something like a hydrogen atom, where it just has that single electron, we would just have a single electron, that one s orbital. And if we excited that electron, we could promote it to a higher energy level. Eventually, it would relax, it would release that, it would emit that energy again, like we talked about in the previous section. But with the hydrogen atom, what we're going to see is all of the orbitals on a given energy level are going to be what's known as degenerate, meaning that they're going to be equal in energy. So that's why we just have them going straight across for everything on the 2 energy level. Same thing for n equals 3. 3s, 3p, and 3d are all just right in line with each other because they're going to have the same energy. And of course, as we go from 1 to 2 to 3, now they're increasing in energy, but everything in the 3rd energy level or everything in the 2nd energy level is going to be equal. But what we're going to see with other atoms is once we start to introduce multiple electrons, now instead of just the attraction between that one electron and the one proton in the nucleus, now we're going to start to have repulsion between those multiple electrons. And what we're going to see is that's actually going to affect the energy level of these different orbitals. So we're going to see the 2 p orbitals are still going to be all degenerate with one another. Same thing with the 3d orbitals. But now they're not going to be the same as each other. So we can see 2s and 2p are different. Same thing with 3s, 3p, 3d. And we'll actually go through some of the weird things that are going to happen now that we can see, like 4s is actually going to be lower energy than 3d here. And then with the final quantum number, so that spin quantum number, m sub s, they were ultimately able to determine that no two electrons, so even in the same orbital, have exactly the same energy. So what we do to distinguish those two is just have that final quantum number. And with it, it's just referring to the spin. So that's going to affect the magnetic field. It's going to affect slightly the energy. And we just refer to it as, again, positive 1/2 or negative 1/2. Oops, I don't know why this is coming up here. Oops. Okay, so this. So if we're looking at the an energy diagram for electron orbitals, again, we've got the energy going up. So if we're looking at the first energy level here, n equals 1, that means L is going to have to be equal to 0. So what we're going to see is that we'll just have that single s orbital. But now when n equals 2, L can equal 0 or n minus 1. So 2 minus 1 just gives us 1. And then the same thing with one more step there at n equals 3. So like I said, with the first energy level, L equals 0. So m sub L, and I can write this on it so we can see it as we're going here. Where is the pen? There it is. So this will be 0. So 0 to n minus 1. And then this is negative L to positive L. L didn't come out great, did it? That one didn't come out much better, but we'll just get that. So again, with the first energy level, we'll just have that single s orbital. And then when we get to the second energy level, we'll still have an s orbital there. L equals 0 can only have that single orbital. But now with L equals 1, we're going to see the p orbital. So again, we'll have 3 of those there. So it can be negative 1, 0, or positive 1. And then the same thing with the third energy level. Oops. But now we'll also have the d orbitals available. And the L kind of got a little covered there. But now we'll have the d orbitals, which are going to have 5 because if L is equal to 2, we can have m sub L equal to negative 2 all the way to positive 2. And again, we've got to account for 0 there. So that's why we're going to have 5 orbitals. Oops, and these slides just got a little mixed up. So this should have gone back with the magnetic spin there. But the reason we have that spin quantum number to distinguish the final two is just because we can't have any two electrons that have exactly the same set of quantum numbers there. So we can have 2 electrons in the same orbital, but the distinguishing factor between those two then would just be this final quantum number, this magnetic spin. One of them would be positive 1/2, one of them would be negative 1/2, just to distinguish the two. And then as we start to go through this, we'll see more of these energy diagrams. But as we start to actually fill these in, instead of just having the lines representing the orbitals here in red, we can actually place electrons in these, and an orbital is going to be able to hold 2 electrons. So that's why if you think about the periodic table, that first period just has hydrogen and helium, because the first energy level can only hold 2 electrons. But as we start to add these electrons, we'll use arrows to represent them. And to represent the difference in that magnetic spin, because if you think about it, the other 3 quantum numbers are going to be the same, 1, 0, and 0 in this case. To represent that electron spin, we just have one of the arrows pointing up, the other one pointing down, just to show that they're going to be different electrons. And with it, typically, I put the one pointing up first, but you can put the one pointing down first as well. It doesn't really matter too much. Okay, so with this one, if you want to practice on your own, feel free to do that, but write the set of quantum numbers which describe each electron in the 3 2p orbitals. So with that, we'd be thinking about the electrons describing or the quantum numbers describing the electrons for boron, or the final electron, I should say, for boron, carbon, nitrogen, oxygen, fluorine, and neon. So if you want to practice on your own, feel free to do that. But I'm just going to go ahead and kind of do this. But with this, we're going to see with you the 2p orbitals. We're going to be looking at n equals 2. So with L, what that could be is 0 or n minus 1, or it could go up to n minus 1. So it could be 0, or in this case, 2 minus 1. So it could be 0 or 1. 0 is going to be representing the s electrons. So we want L is equal to 1 there. And then we'll have m sub L for the magnetic quantum number. This can be negative L to positive L. So this could be negative 1. Or this. Or it could be positive 1. Or it could be 0. And again, we're just skipping the 2s electrons because we're only interested in the 2p for this one. But we could also have n is equal to 2, L is equal to 0, and then m sub L would have to only be equal to 0. But in this case, the p electrons are going to have 3 sets of orbitals. And then with the final piece, can I do plus or minus? Equals or minus, plus or minus 1/2. Same thing. So for each of these orbitals now, they can all hold 2 electrons. And again, the electrons themselves can't be exactly the same. You're going to have slightly different energies, and we're going to represent that with the spin there. So we could have, for the p electrons, we'll have n is equal to 2, L is equal to 1 for all of them. But then since we've got 3 different orbitals, the orientation of those is going to be different. So that's why we've got m sub L, negative 1, 0, or positive 1. And then with each of those orbitals, can be 6 electrons, or it can hold 2 electrons because we've got 6 total. So to distinguish between each of those electrons in the 3 orbitals, we just have positive or negative 1/2 to represent the spin there. Oops, and I didn't actually put it, but that should be m sub s is equal to positive or negative 1/2. And then looking at these 4 sets of quantum numbers, take a moment or two to kind of go through it on your own. Again, you probably want to pause the video because I'm just going to sort of continue through it. But look at these 4 quantum numbers and think about which of these is going to be acceptable. There may be multiple, there may be none. So go through each of them. Think about how each previous quantum number is going to affect the next. So think about if n is equal to 1 or 3 or 2, what that means for L. And then based on what L is, think about how that's going to affect m sub L. So think about how the angular momentum is going to affect the magnetic quantum number. But again, you're going to want to pause it because I'm just going to start going through these ones. But with the first one, n sub 1, and we should say, so n can be just any whole number greater than 1. So all of these are fine. So we're going to want to start examining them at the L, that angular momentum quantum number. But with L, I can write this in as well, L has to be equal to 0 through n minus 1. So 0 to n minus 1. So with the first one, that's automatically a problem because on that first energy level, we can only have L equal to 0. So we can already disqualify this one. With the bottom 3, though, those are all fine because if n is equal to 3, could be 0 to 2. That works. N is equal to 1, it has to be 0, but that's still fine. And then if n is equal to 2, it could be 0 or 1. So all 3 of these angular momentum quantum numbers at for 2 through 4 are fine. So now we've got to examine them based on the magnetic quantum number. And with the magnetic one, change the color. With this, it can be negative L to positive L. So for the second one here, 0, negative 0 to positive 0 is just 0, but that's fine. Third one still has L equals to 0, so the magnetic quantum number would have to be 0. That's not acceptable. That won't work. And then the same thing with the fourth one. If L is 1, M sub L has to be either negative 1, positive 1, or 0. Can't be 2. So with these four quantum number, or these four combinations of quantum numbers, the only one that'll actually be acceptable is just that second one. Yep. And then again, these are just highlighting what the error is. So if L was equal to 1, we could have this magnetic quantum number here. But in that case, we would need n equal to 2 or 3 or anything greater than 1. So that's the problem there. Okay, and then with this next one, I think this is the last practice one for these types of ones. We want to actually write the set of quantum numbers that describe all 10 electrons in neon. So neon's atomic number 10, it's going to have 10 protons. Means it's also going to have 10 electrons just to balance the charge there. And with it, we can go through and actually write the quantum numbers for all of those. So if you want to go through this on your own, definitely feel free to pause the video and do that. But I'm just going to start going through them. And again, we're going to have 10 electrons in total. So that's why I just got that filled in here. And then with these, we just have the four different sets of quantum numbers. So with the first one, we'll of course have n is equal to 1. L has to be equal to 0 in that case, which means M sub L also has to be equal to 0. And then we could have positive 1/2. And we only have that first, we only have a single orbital in that first energy level. But each orbital can hold 2 electrons. So we could also have a negative 1/2 for the spin there. But that's all we're going to have for the first energy level. And with the rest of these, it's all just going to be 2. So we can just go ahead and fill all those in. But with that, that means M sub L can be 0. And again, we'll have 2 electrons there. Or it could be equal to n minus 1. And the reason I put 1 and 6 of these spots here is because if 1 is our angular momentum quantum number, that means M sub L, and this should really be lowercase m and then the subscript L there, could be negative 1, could be 0, or it could be positive 1. And then again, each of those electrons, or each of those orbitals can hold 2 electrons. So we'll just repeat that pattern again. And then with this, we'll see we'll have positive 1/2. And then typically we'll see this a little bit easier with the spin when we actually look at the electron orbital diagrams a little bit more. But before I said it doesn't really matter if the first electron is pointed up or down. But if we've got the first electron pointed up, and then we're going to be adding other electrons to different orbitals, we're going to want the first electron also pointed up for those. So that's why the first 3 here are all going to be positive 1/2, because each of these are going into a different orbital. So they're all going to be 2p orbitals, but they're going to have that different orientation. And then with the final 3, they'll just have the opposite spin. So they'll be negative 1/2. But they'll be going in those same three orbitals. It's just now if we think about the arrows pointed up or down, the first 3 are all going to be pointing up. The last 3 are all going to be pointed down. But we'll see we'll have a combination of those in each of those orbitals. Because if you look, negative 1, negative 1, well, you've got positive 1/2, and then negative 1/2, and then the same thing for the other 2 there. And then with the 2s orbitals, or 2s orbital, I should say, because it's just the 1, we can only have a magnetic quantum number of 0 there. So we'll just have the magnetic spin of positive and negative 1/2. And then, like I said, we've kind of already talked about this a little bit, but with the elements as they get a little bit larger, as we go from increasing from atomic number of 1 to 2 to 3 to 4 and so on. We're adding an additional proton. That's why the atomic number is increasing. But with that, the atoms themselves are going to be neutral. So for each positive proton we're adding, we're going to have to add another negative electron as well to balance it out. And what we're going to see is as we do that, there's going to be a certain pattern in terms of how we fill these in. And with it, we kind of just saw it with that neon one. But there's going to be a pattern for how we go through it. But with it, just to go back here, I can't. With these are going to be known as orbital filling diagrams or energy diagrams of orbitals. So there's a couple of similar terms for it, but it's essentially just going to be showing us how the electrons are sort of distributed into all of these different orbitals here. But with it, sometimes we'll see boxes instead of just the line for the orbital. But with it, each box is just going to represent a single orbital. And then each of these half arrows, sometimes you'll see full arrows like right here. But the more common version is with the half. And if you think about it, positive a half, negative a half. So that's why we've got the half arrows there. But each of these half arrows is going to represent one electron. And then since they're going to have the different spin, that's why if we've got two of them in the same orbital, we'll always want to make sure one of them is pointed up and one of them is pointed down. We'll actually have a specific rule for that. And we can kind of see the pattern we're going to start to want to use at least as we look at the first couple elements here. So as we go from hydrogen, which just has the single electron, so it'll go in 1s. Helium has a second, so now we just have that second one pointed down. We go to lithium, so we move to 2s. Beryllium, we have the electron pointed in the opposite direction now. And then boron, we continue through there. And if we look at these, 1s, 2s, 2p. So in addition to showing this electron configuration, is what it really is, just how those electrons are set up in the atom, how they fill in those different orbitals. We can show it with these orbital box diagrams, or we can do the spectroscopic notation, which is actually just kind of writing it out. So with hydrogen, it's 1s1, helium 1s2, and then so on for these bottom ones. Because with this, the number out in front is representing the energy level, so it's representing N. S or P, or if we had D or F or whatever it's going to be for the particular electron that we're looking at, that letter is going to represent the orbital. So S is going to be spherical, P is going to be kind of the dumbbell looking shape. D is going to be kind of two p orbitals combined, but that's going to tell us the shape of the orbital. And then the exponent, so 1 or 2, with P we could have up to 6, with D we could have up to 10, but whatever that exponent is then telling us how many electrons we have in that subshell. So with the S subshell, since it's just one orbital, we can have up to 2. But then with the P subshell, since it's going to be 3 orbitals now, we could have up to 6. And like I said, with the D orbital, since it's got 5, or with the D subshell, I should say, since it's got 5 orbitals, it could go up to 10. But with this, it's essentially just listing out the order in which these electrons are going to fill in. And with it, we'll see that as we add additional electrons, they're always going to fill in from lowest energy to highest. So for the most part, this pattern is always going to be exactly the same. It's just going to kind of depend on where we're actually going to stop. So with boron, we stop at the 5th electron just because it's got an atomic number of 5. But we'll see the electrons are pretty much going to always fill in the exact same order, just up until the amount of electrons that they actually have in that atom. But we'll also see just a few exceptions with that one, because with chemistry, there's always going to be a few exceptions pretty much with every rule. But going back to these diagrams for a second, with it, there's going to be a couple rules in terms of how we fill these in. Because if we think about carbon, for instance, it's going to have 6 electrons. So 1s2, 2s2, and then 2p2. So if we think about the orbital diagram here, there's going to be a couple ways we could fill it in. You'll see we've got 1s and 2s completely filled in with the 2 electrons in each of those orbitals. But then when we get to 2p, now we've got 3 orbitals in that subshell, and they're all going to be degenerate. They're all going to be equal energy. So when we go to add electrons to a subshell that has multiple orbitals, so p, d, or f, what we're going to do is like we have up here. We're going to do what's known as singly occupying each of these orbitals. So we'll put one at a time before we then come back and double them up. And one kind of analogy you can use is, or at least I've seen in some textbooks, is with like a hotel room floor. So like I have 2 brothers. So if we're going to fill in a hotel room floor, if the rooms were open and if we could afford it, of course, we would want to each take our own room. So if we had 3 electrons here in these orbitals, sort of representing me and my brothers in the hotel room, we'd want to go into our individual rooms. And then if we had a 4th sibling, so if my sister was also there, then somebody would have to double up. But we wouldn't just put 2 people in that first room automatically. Again, in this case, we're assuming that we actually could afford all the different rooms. But with it, the electrons are going to be kind of the same, where they want to be spread out until they have to have that second electron in the orbital. So that's why if we look at oxygen now, atomic number of 8, so it's going to have 2 additional 2p electrons. So now it's got 4 of them here. That's going to be where we start to see them double up. So if we were actually filling this one in, the way we would go is we would do 2 in the 1s orbital, because we're going to completely fill in the energy level before we move to the higher one. Then we'll put 2 in the 2s orbital. But when we get to 2p, we'll do 1, 2, 3. So we'll put 1 in each of those orbitals. And then we'll put a 4th one there. And with this, another way you can think about it is electrons are all going to be negative, so there's going to be a repulsion between them. So if we, instead of going 1 at a time, immediately put 2 in this first 2p orbital, now we're going to have those 2 negative electrons relatively close together. So we're going to have unneeded repulsion there, which is just going to cause higher energy overall. So it's just going to be a little bit more unstable than if we spread those electrons out. And then with this, you can see the pattern a little better now as we go through the entire 2p subshell, starting with carbon. So we're missing boron, where it's just got the first one there. But then with carbon, we've got the second one. So now we add it to the second orbital, nitrogen, the third. And now with oxygen, we start doubling up. Same thing with fluorine. And then with neon, now we've got a fully occupied 2p subshell. And then with this, we've got this little diagram that's going to kind of show us exactly how these are going to fill in. And then we'll be able to see on the periodic table exactly why it's going to be like this. Because you may think it would just go 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d. So you think it would kind of just go horizontally like that. But what we're going to see is it'll go 1s, 2s, 2p, 3s, 3p. But then instead of going 3p, 3d, we're actually going to fill in the 4s first. Then we'll go back to 3d, 4p, 5s, 4d, 5p. So it's going to be a little bit offset. But when we look at the periodic table, we'll be able to see exactly why that is. Okay. And then with this one, if you want to go through and practice these ones on your own again, like always, just pause it, because I'm going to kind of just go through and do it right away. Yes, do a little bit more space. All right, so we've got 1s, 2s, 2p, 3s, and 3p. So with aluminum, what is that? Atomic number 13. So what we're going to see with aluminum is as we fill these in, oops, I didn't mean to do double arrow on that one. Oops. We'll put the first 2 there, next to in the 2s orbital, and then when we get to 2p, just like we saw, we'll do one at a time. So we'll have all three of these pointed up first, and then we'll start doubly occupying each of these orbitals. And then with the 3s, completely fill that in before we move to the next energy level. And then with aluminum, it's just going to have a single electron in that 3p. So we'll just have to put the first one there. And then with this, just so I don't have to redraw everything, I'm going to go through and do the same thing and just kind of have it continue for arsenic. So what I'll do is change the color so we can see at what point does aluminum go up through, and then how is arsenic going to fill in afterwards. But with arsenic, we'll also need, oops, and I'm going to use a different color just so it's a little bit easier to see. So let's go with green. Yeah. So with arsenic, we'll also need the 4s. And then with the periodic table, again, it's going to be a little weird, and we'll see exactly how we can use the periodic table itself as a tool to kind of remember the order of these. But then with the fourth period, we're going to see it starts with 4s, but then we've got the D block in the middle, so we'll actually have 3D in this case. Because remember, if L is equal to 3, that means M sub L could be 0 to 3 minus 1, so it could be 0, 1, or 2. So we've got 3s, which is 0, 3p, which is 1, and then 3d is going to be 2. And then we'll also have, on that fourth period, just the 4p. So with these, again, this is for aluminum with an atomic number of 13. Arsenic is going to be an atomic number of 33, but it's still going to start the same. So that's why I'm just going to have this continue. But then with arsenic, whoops, we don't want to do two of them in there. Arsenic, we'll just fill in the 3p orbitals with one electron, and then we'll start adding that second one in there. 4s, again, only has that single orbital, so we'll just put 2 in there right away. And then the 3d, we're going to treat just the same as we did the p orbitals. It's just in this case, we've got 5 of them. So we'll put the first 5 electrons in each of those orbitals. And then we'll put the 6th, the 7th, all the way through the 10th. In those as well. And then with arsenic, we're going to have 3 more electrons. So we're going to see it'll just be 1, 2, 3, like that. And then with the spectroscopic notation, we've essentially already got it as it's shown here. Because the only thing we would need to add now, we've already got kind of the order of these. We would just need to add the exponent to show how many of them we actually have here. So for 1s2, 2s2, 2p6, 3s2, and then for aluminum, it'll be 3p1, and that'll just be where it stops. But for the arsenic, so again, I'm going to do the different color. I'll just write it next to it. But the 2s, 2p part is going to be the same. And we'll see that since these are going to fill in the same order, the exponent for all of these up until the point where we've got additional electrons is going to be the same. So 1s2, 2s2, 2p6, 3s2. But now when we get to the 3p orbitals, we don't just have a single electron there. Now we've got 6 of them. And then we want to continue. So 4s2, 3d, and again, just how many electrons do we have there? So 3d10. And then with the p orbital, we'll just have a 3. Oops. All right. But like I said, we can use the periodic table itself as a guide because we've kind of got natural divisions in the periodic table. So we can kind of see where these different blocks are going to be. And I'm referring to them as blocks because we've got the S block, the P block, the F block. And then it's labeling it transition metals here, but that could also just be the D block because that's going to be where we see these different orbitals or where the electrons like as we're writing in that or writing out that spectroscopic notation. we can kind of use this to see where those electrons are going to be located as we go from the elements to the next element. But on the left-hand side, we're going to have the s orbital, and we'll see it's only going to be 2 groups wide because those s orbitals only have one orientation. So there's only a single s orbital for each energy level, and each orbital can only hold 2 electrons. So that's why we've only got two groups in this s block. And then with helium, we'll see, you can kind of see where helium would really fit in here. But when we go through chapter 7, we'll see exactly why we actually include helium on the right-hand side here. But with the cutout here, you can see kind of where helium would fit in terms of the spectroscopic notation. And then on the right-hand side, we've got the p block. And again, each orbital can hold 2 electrons, but we've got 3 p orbitals. So that's why the p block is going to be 6 groups wide. And with the s and the p, you'll notice that the energy level, so that number out in front, 1, 2, 3, 4, 5, matches up exactly with the period that it's in. So when we're on the left or the right-hand side, the period is going to match that energy level. But then when we go to the middle of the periodic table, we've got this d block. And again, the d block has 5 orbitals, so that's why it's going to be 10 groups wide. We can fit 10 electrons in that d block, or in those d orbitals. But what we're going to see now, and if we think back to the way that sort of that weird chart with the arrows filled in, the d block is going to be 1 less. So we go 3s, 3p, then go down to 4s, but then we temporarily come back to the 3d. So with the d block in the middle, it's always going to be, the energy level is always going to be 1 less than the period. And then with the f block, let me get the draw tool going. We've got 2 groups here. These are actually going to fit right into these spots. So you can kind of just squeeze it in there. But the reason we leave these off is because, or we kind of separate them out, is because these are going to be f electrons. So that's why we've specifically chosen these groups here, or these elements rather. But it's going to fit right there. So what we're really going to see is the periodic table itself is then going to get stretched out a whole bunch from left to right. So it would just make it really hard to read. It'd be really hard to fit on a piece of paper or something like that, while also being able to include like the symbol of the element, the atomic mass, and things like that. So we separate out the 2 periods at the bottom here, just to make it a little bit easier to read the periodic table. But they actually fit in right here. So that's why as we're looking at the spectroscopic notation, we'd go 5s, 4d, 5p, 6s, and then we'd go 4f up to 5d, 6p, 7s, down to 5f, pop back up to 6d, and then 7p for the end. But again, we can kind of use the periodic table itself because we can see the s block is just going to be the 2 off to the side. The p block, we can kind of see we've got this natural sort of divider in the middle. So the p block is just going to be the groups to the right here. The d block will be in the middle, and then the f block is just separated off by itself at the bottom. But also with the f block, like I said, it fits into these two spots here, which means if we look at the number, it'd be 6f and then, or 6s, excuse me, and then 4f. So we're going to see the d block is offset by 1. The f block is really going to be offset by 2. And with this, you can always just also look at the atomic number itself. So with, what is that going to be? With this one here, we'll see barium 56. You can always just follow the atomic number to kind of see where this is supposed to jump to. Because the atomic number is still just going to go up by 1 each time, so you can see where we're supposed to actually, when we're supposed to actually hop down to this spot just by looking at the atomic number. Or the same thing with the final row when we go from 7s, so francium and radium, down to, it's going to be thorium, I think, or actinium, rather. But where is But with it, we just saw that the D block is kind of weird because it is offset by 1. So as we go from like potassium and calcium, so 4s, 4s2, we go to 3D in the middle here. We'll see that there's going to be a few sort of exceptions in terms of the way that these electrons are going to fill in. And with it, it's going to be with things like copper. That's it correctly, should not be copper. That would be chromium. It should be chromium. We will see, whoops, we will see an exception with copper, but that is not the one that we're looking at right here. But looking at the way that the spectroscopic notation is written is another thing to point out. So if we think about writing out the electron configuration, that spectroscopic notation, it could get kind of tedious and kind of annoying if we've got to have a lot of electrons, especially since the inner ones are going to fill in pretty much the same order all the time. So what we can do to kind of shorten that a little bit is look at the element we're interested in. So in this case, chromium. What we can do is go up one period and then go all the way to the noble gas. So just go up one row all the way to the right-hand side and just put that element in brackets, because putting AR in brackets now is going to represent 1s2, 2s2, 2p6, 3s2, 3p6. So it represents all of the electrons up till number 18. And then we can just continue from there till whatever spot we need to stop at. So in the case of chromium, we could just go 19 through the 24th electron. But with this, with chromium, we may expect after 3p6 to go 4s2 and then 3d4. But what we're going to see is we'll actually have 4s1, 3d5. And the reason for this, and we'll also see, like I said, copper is going to have an exception. Instead of 4s2 and 3d9, we're going to take one of those s electrons and move it to the D block. So we'll have 4s1, 3d10. And the reason we're going to do this is because the energy level of 4s and 3d are going to be very, very close. But also the electrons are going to be the most stable. Oops. Yeah, so we already had, I skipped through it a little bit. But the electrons are going to be most stable when the orbitals are either empty, full, or half filled. So if we look at chromium, 4s2, 3d4 has a completely filled 4s orbital, but then the 3d is 40% filled. But now if we take that, take one of those s electrons and move it to the D block, now we get a half filled and a half filled. So that's just going to be a lower energy overall. So that's just going to be a better sort of setup for the electrons. And then the same thing with the copper. So if we look here, copper is 29. So you'd kind of expect it to be 4s2 and then 3d9. But if it was 4s2 and 3d9, it'd have a completely filled s electron or s orbital, and then a 90% filled d orbital, d subshell. And again, it's the best if it's either empty, full, or exactly half filled. So if we take that s electron, or one of those s electrons rather, and move it to the d subshell, now we completely fill in the d block and have the s block half filled in. So that's why we'll see exceptions in some cases with things like chromium and copper. And then with these ones, again, if we think back to the orbital diagrams, once we start to have multiple electrons, the repulsion between those affects the energy of those different subshells. So that's why we actually see 4s is going to be lower energy than 3d, but they're going to be very close in energy. And that's why we'll be able to kind of have the electron move to the 3d d orbital instead. And then with this, if you look at silver underneath copper, it's the same thing. We're just one energy level higher. So instead of 3d10 4s1, now we have 4d10 5s1. And then this periodic table is just reversing the order that we would typically write those in. But same thing with molybdenum under the chromium. 4d5 5s1. But then with the final two rows, you don't see it all the time. You can still see it with gold. So 6s1, because then we can have the F and the D block filled in. But if you go under molybdenum for tungsten, we've got 5d4. So the s electron, or both s electrons, kind of still stay there. So in the 6th and the 7th row, it's not exactly the same, but we can still see some of those anomalies. And with it, we would see similar things in the F block as well. But with the F block, we're typically not going to be really doing too much with it. We'll mostly be focused on the upper portion of the periodic table here.